it over a two-dimensional shape, and now we're going to integrate our sum over a three-dimensional shape. Now we won't go into the thing too much, but basically it works analogously. So you kind of cut your volume up into little volumes dv, and you basically sum over them. We'll see, I think, more with examples. So examples would be if rho is, now this is the normal density, just mass per unit volume, then the integral of rho dv will be the mass. We're just going to work with triple integrals over boxes and cylinders. We'll keep things simple. And what am I about to say here? I'm about to say, okay, we need to understand what this notation means. So this notation means if you have an x-axis, a y-axis, and a z-axis, the first pair of numbers is going to refer to the x-axis. So you're talking all the points whose x-coordinate is between 0 and 2. The second pair of numbers corresponds to so this will be 0 for all of them, the y-axis, or the y, so you're looking at all the y values between 0 and 3. And the last one then is the z values, so you're looking at all the z values between 0 and 4. And if you take kind of all, so basically that means all points where I think it means all points where the x-coordinate is less than or equal to 2 and the y-coordinate is less than or equal to 3 and the z-coordinate is less than or equal to 4. And if you have a think about it, this will actually make up a three-dimensional box, which I wonder if I have a picture on the next page. Yeah. So this is the x and y is a bit mixed up. So the x goes from 0 to 2. So this should be x, this should be y, and this should be z. So you can see the x is going from 0 to 2. The y is going from 0 to 3. Now it looks like it's going from 2 to 3, but it's actually not if you look at it a bit more. And the z is going from 0 to 4. And so all of the points in this, the x coordinates between 0 and 2, check. Y coordinates between 0 and 3, check. Z coordinates between 0 and 4, check. If you take all such points, you get a cube. Okay. So what we're trying to do is find the mass of this box if the density is given as 2xy squared z cubed and assume SI units. So we're going to find the mass of a horizontal strip. Now, how will this work? So it said we're fixing, what did it say we're fixing? Fix y and z. So fix a height and fix a y coordinate. So say, for example, you fixed z equal to 2 and y equal to 1. If you can imagine a strip going across this, so how do you think about this thing? So so this is going to go across here. So it's a strip. It is parallel to the x face on the left. It's perpendicular to the y face, and I suppose it's kind of parallel. Yeah, so you can see here that the x coordinate is changing from 0 up to x equal to 2, but the y coordinate is constant. It's whatever, it's supposed to be equal to 1 here, and the z coordinate is constant. So if you can imagine, so yeah, it's probably hard to imagine this. So imagine you've got a shed in front of you, and you've got these kind of matchstick planks, and you just fill up the shed with these matchstick planks. So these are, the cross-sectional area is the same. It's probably easier to draw it like this. These are all supposed to be straight lines. So that's a plan. So you can pull out one of these strips. So you pull it out, and it'll have a length, in this case, of x equal to 2. Sorry, of 2. But its other dimensions are very, very small. The dimensions of this would be dz, and the dimension of this is dy. and we'll find the mass of that. So yeah, you're thinking like a matchstick or something like that, but it goes from x equals 0 to x equals 2, and actually here we're assuming SI units, so it's 2 meters long. Okay, so I think what we're going to do is we're going to hopefully be able to do that on the previous page. So we're adding up. So the mass of a strip is, you're adding up. Now I'm going to write some things and then I'm going to get rid of them. So you're adding up from x equal to 0 to x equal to 2, and you're adding up, what are you adding up? This rho xyz, so that's the density at xyz, which is 2xy squared z cubed times the volume. So the volume is a little dx, dy, dz. I might show you a little volume element on the next page. So if you just chop across this, I'll do it in the middle. That's a little volume element. And you see you've got the dz is the vertical, dy is the horizontal, and then this last one is dx. So the volume of this is dx by dy by dz. That's the little volume of these. Now, the dz and dy are supposed to be very, very small in a certain sense. Okay, so what we have here is we're adding up actually infinitely many small things. So that's an integral. So that was the thing we were going to get rid of. And we're adding up from x equal to 0 to x equal to 2. Now, as x is varying, y and z are constant, so anything that isn't x can be taken out as a constant. So 2y squared z cubed dy dz. So if you go back and look at that matchstick, the dy and the dz are constant. Now you might say, oh, the dx is constant as well. Well, don't worry about that bit. Okay, and then we're left with integral from 0 to 2 x dx. So this is not too bad. What's the integral, or what's the antiderivative of x? Well, x is x to the 1. So we're going to keep, and if you want, you can get a bit lazy and you can say, oh, let that be alpha. Find that to be alpha. I'll just do this once, just show you there is a shortcut. So you say, oh, that's alpha. So you just write alpha. And then you can write, what's the antiderivative of x to the 1 is x squared over 2. From 0 to 2, and remember you do top limit minus bottom limit. So alpha, which isn't a constant here, it's actually a function of y and z, and probably dy and dz as well. So you get 2 squared over 2 minus 0 squared over 2, which is equal to 2 alpha. And we can write out what alpha is then on the next page. So that's the mass of a strip, is 2 times this 2y squared z cubed. If you want to be lazy, I won't be lazy anymore after this. It was just helpful here the way I ran out of space as well. So the mass of a strip here is, and of course it depends on so what was it, 2 by alpha. Now alpha had a 2 in it already, so 4y squared z cubed dy dz. Now you'll notice that where the y and z coordinate are says how heavy the strip is, because the density depends on x, y, and z. So now what we're going to do is we're going to fix z, so we're going to fix the height, and we're going to add up all of these kind of matchstick planks from y equal to 0 here, the whole way across, and at a fixed height. So this is like adding up, say, all of these. So you understand this is a plan. So it's actually like that. So if you add up from, say, this would be y equal to 0 to y equal to 3, all those sticks, you're getting the mass of what you could call a plate. Okay, so this thing, I know it doesn't look like, but that's only because I'm crap at drawing. Oh, geez, that worked out well. So if we add up the mass of the strips from, let's write this in, from here, this strip, which is at y equal to 0. Okay, we can't see that. Up to the strip here at y equal to 3, we'll have the mass of a plate at a height z. So, mass of plate is equal to add up. Now again, I'm going to get rid of this sum. So add up the mass of the strips from y equal to 0 up to 3. And the mass of a strip is 4y squared z cubed dy dz. As I said, I was going to get rid of the sum. So here you're adding up infinitely many infinitely small things. That's what an integral is. We'll fix anything that isn't, so only y is changing now. So anything that isn't y can be taken out as a constant. So 4 z cubed dz. And we're left to integrate y squared dy. Okay, so integral of y squared dy is no bother. Add 1 to the power, divide by the new power. So y cubed over 3 from 0 to 3. Top limit minus bottom limit. So we get 4z cubed dz, 3 cubed over 3 minus 0 cubed over 3. And 3 cubed over 3 would be 3 squared, which is 9. And the 9 by the 4 gives us 36 z cubed dz. So you can see that the mass of the plate depends on the value of z. So now to get the mass of the box, you add up the mass of all the plates, and the plates go from the bottom plate, which is the z equals 0 plate, all the way up to the z equal to 4 plate. So you're adding all them up. And if you add all those plates, the mass of all those plates up, they're all infinitely small because they have infinitely small volume. You get the total. So like you're adding all of the plates up. Okay, let's do it. So the mass of the box is equal to, and now I won't do the summing anymore. So add up from z equal to 0, because that's the bottom one, because z goes from 0 up to the top one. Z equal to 4, 36 z cubed dz. Now we don't really have to bring out the 36 here because we can just fix it as a constant. And what's the antiderivative of z cubed? Z to the 4 over 4. And we're going with top limit minus bottom limit. Probably going to need the calculator here. So substitute in. Now we might do, yeah, well, we could do 36 over 4 is 9, but I won't bother. Let's be a bit lazy. 36 over 4. Substitute top limit 4 to the 4 minus 36 over 4. Substitute bottom limit 0 to the 4. And the 4 to the 4 over 4 is 4 to the 3, which is 64 by 36, giving us 2,304. And the question said assume SI units, and the SI units of mass are kilograms. Okay, so that's that. I think we'll just keep on going, or no, we'll stop there. No, we'll keep going. The other thing that we're going to look at is cylinders. So with cylinders, it's going to be a similar story. Now, what's going to be different is you're changing using polar coordinates for the x and the y. So any x's in a cylinder, if you just look down the bottom, they're just, it's like the polar coordinates, the circular coordinates you saw in last week. This would be r cos theta, y would be r sine theta. Now you've got to think about a volume element. I don't know if I have a picture on the next page. Here's your volume element. So what we would have shown in the previous section is that the area element, this would be a little kind of a pizza slice, or a pizza piece, sorry, pineapple piece. So we showed that the area, so that would be this bit, is r d theta. And so the volume will be that area by the height, which is dz. So you get r dr d theta dz. And that will be the volume of that little pineapple piece. Okay, so I need that on the next page. So dv, so if you're integrating over a volume, the way you chop it up, so with the box, you essentially chop it up into loads of little squares. And then you add up the squares, you get a matchstick. Add up the matchsticks, you get a plate. Add up the plate, you get the box. It's going to be different here. Now, there's 6 different ways that you can do it that are different. I might just draw the 6 of them for you. So, but here anyway, we got so r dr d theta by dz. Okay, so the way I'm going to recommend is first, so imagine all these little pineapple pieces. So first you're going to find the contribution to the sum from a spoke. Now, a spoke, its r is changing, and theta and z are fixed. Then you're going to add up all the spokes from x equal to 0, which looks something like that, to x, from theta equal to 0, theta equal to 2 pi. So then the disk is at a fixed height. And then if you add up the contribution to the sum from all the disks from the lowest height to the highest height, you have the contribution over the entire sum. And it's going to be a mass. So we're going to be able to talk about the mass of a spoke, then the mass of a disk, and then the mass of a value. Now, you don't have to do spoke, disk, cylinder. There are other ways, so I'm going to show you those other ways. Okay, so here we're going to describe the different ways, depending of kind of finding the mass of a cylinder using integration. So there's actually 6 different ways, and it corresponds to the different orders that you differentiate. Say the first one we're going to look at is r, then theta, then z. So now I'm going to try and draw cylinders here. Maybe I should, yeah, no, I can draw a cylinder, can't I? Do you believe in me? Unreal. Not bad. Looks a bit like a pint glass. Right. So here's the z-axis going through it. The x and the y-axis are not so important. So the first way that we looked at is you fix a height. Okay. Oh, I do need the x and y-axis because you need to fix an angle as well. So pick an angle there. That does, no, which one would be x and which would be y? I think this is x and this is y. That might be wrong. So the angle is with the x-axis. So fix an angle, fix a height. So you get something that goes from the central axis out to the edge of the cylinder. And that's adding up from r equal to 0 up to r equal to the radius of the cylinder. Then what you do next is you add up the mass of all those spokes from theta equal to 0 all the way to theta equal to 2 pi. And then you get the mass of a disk. And then you add up the mass of the disks all the way from, let's say z is equal to z0, which is the bottom height, all the way up, add them all up, and there's infinitely many of them, up to z equal to z1. So that's the first one. So this one corresponds to spoke, disk, and then the last one's always going to be cylinder. Okay, so what about if we do r z theta? Or z and then theta. So if we're doing r first, the initial setup is going to be the same. You're going to be finding the mass of a spoke. Now, if you're going to integrate with respect to z, what you're doing then is you're adding up the spoke from here up to here. Now, I don't know what you'd call this. It's a plate, but it's a vertical plate. If you could imagine a book, a cylindrical book, where somehow the pages all come outward. So it's yeah, cylindrical book. It would be a page in a cylindrical book. And then of course, if you add up all these pages from theta equal to 0 to theta equal to pi, you get the mass of the cylinder. Okay, let's look at the next one. Next one, let's say we do theta first. So theta first, then r, then z. So this one, you would be fixing an r and a z. So you're fixing a height, that's kind of easy. And you are fixing a distance. So the r, like a would be the radius of this, or b, so it'd be a little bit. So fix a radius. a distance from the central axis, and then integrate with respect to theta, what you're going to get then is the mass of a ring. Then if you integrate with respect to r, you're going to be looking, you're going to go from r equals 0, so you're adding up the rings, the small rings, and then bigger and bigger and bigger, eventually you get the disk. So if I might write down, this one is spoke, then I'm going to call it page, and then you always finish with cylinder. This one is ring, disk, which I never know how to spell, cylinder. Okay, what's the other possibility? Another possibility, theta z r. So this one starts with a ring, and then you add up from the z's. So you end up with, now what this would be like is a cylindrical shell. It's like a Pringles tin, it's hollow. So you got all these rings. Yeah, so this is, I'm going to go with ring, cylindrical shell. Well, we'll call it a Pringles. Say Pringles. And then, of course, when you add all the Pringles, so the Pringles, some of them are really, really narrow, and then some of them are really, really wide. You get the cylinder. Okay, so have we got, that's 4. So the other way is we can start with Z. So Z, theta, r. So this time you fix a theta and an r. So you fix an angle, you fix a height, not a height, a distance from the center. So fix an angle and a distance, and add up with respect to z first. So that's a bar. Okay, and then you're adding up all the bars from theta equals 0 to t. Then you actually end up with Pringles, I think, again. So you get bar, Pringles, cylinder. So imagine if you add up all the bars from theta equal to 0, and then the other one, the last one, which is z or theta. So you'd start with a bar, so just like a bar in the cylinder, and then if you integrate that with respect to r, you're going to get a page, and then you'll end up with a cylinder. Okay, now I'm always going to recommend mass of a spoke, then mass of a disc, and then mass of a cylinder. So first r, then theta, then z. That's what I'm going to recommend. Okay, so we have a question here. We have a volume. Now we remember from the previous section that this is a squared, in other words 3 squared. So the radius of the cylinder is 3, and the z goes from 0 to 2, so the height of the thing is 2. So for this volume, calculate the mass. So as we said before, we use the parameterization. X is r cos theta, y is r sin theta, and the volume element is given like that. So I'm just going to rewrite the thing we're adding up. So we're adding up rho x, y, z dv. So so rho x, y, z, that's the density at any point is x squared z. So that's x is r cos theta squared z, and dv is r dr d theta dz, and that's what we're adding up. Now we can tidy this up a little bit actually, because r cos theta all squared is r cos theta by r cos theta. The r by r gives us r squared, and there's another r there, so you get r cubed, and then the cos by cos gives us cos squared theta by z by dr by d theta by dz. So we're going to find the mass of a spoke. So mass of a spoke, maybe this one here, fixed height, fixed angle, but r is going from 0, so that's the middle bit, out to the edge where the full radius of the cylinder, which is 3. So we're going to find the mass of the spoke, and this thing, because of the dr d theta dz, is infinitely small, so we're adding up from r equal to 0 to r equal to the radius 3, all of this messing around, r cubed cos squared theta. There is a shortcut with this where you can do all the integrals at the same time, but I won't go through that. because I'd like you to understand what's going on. So for space, we might have to use that alpha notation again, or is it? Oh no, here we go. Okay, so we're going to jump to here. So I'm going to take out what is not, what's constant. So on a spoke, the angle is fixed and the height is fixed. So we'll take out cos squared z and the differentials. Cos squared z cos squared theta z d theta dz, and we're left with integral from r equal to 0 to r equal to 3 r cubed dr. Okay. So it says we could pull out the theta and z as they're constant along the spoke. So this is easy enough to do. I won't use this. You could call this thing something to make your life a bit easier. I won't here. Cos squared theta z d theta dz, integral of r cubed is r to the 4 over 4, and we're going from 3 to 0. So this is cos squared theta z d theta dz, top limit minus bottom limit. So we're going to have 3 to the 4 over 4 minus 0 to the 4 over 4. And 3 to the 4 is 3 by 3 by 3 by 3. 9 by 9 is 81. Divided by 4, 81 over 4 cos squared theta z d theta dz. Okay, so now what we're going to do is that's the mass of a spoke, and the spokes, if you pick different angles, you get different spokes. So for example, cos or theta equal to 0, you get that spoke. Theta equal to pi over 2, you get that spoke. Theta equal to pi, you get that spoke. Theta equal to 3 pi over 2, you get that one. Pi over 6, you get that one. And we're adding them all up from theta equal to 0, which is here, all the way around to theta is equal to 2 pi. And that then will be the mass of the disk. So the mass of the disk is add up from theta equal to 0 to theta equal to 2 pi, the mass of a spoke. And the mass of a spoke, we just calculated, was 81 over 4 cos squared theta z d theta dz. And now we'll notice added for a disk, the height is constant. So z is constant. Anything with z can be taken out as constants. So I'll take out 81 over 4 as a constant. I will take out z as a constant, and I'll take out dz, and I'm left with the integral from 0 to 2 pi cos squared theta d theta. Now that the integral or the antiderivative of cos squared is in the tables, but we won't mess around with that. I'm just going to give it to you in the question. Look, integral of cos squared from 0 to 2 pi is pi. So this integral is just pi. So we have 81 over 4 z dz by pi. So that's the mass of a disk, and as you can see, as z gets bigger, it gets bigger. So if we add up the mass of all the disks from the bottom here, which is a height of 0, up to the top, which is a height of 2, we'll have the mass of the cylinder. So finally, the mass of the cylinder is found by adding up from z equal to 0 to z equal to 2, the mass of a disk. So there was a pi in there, a z, and a dz. So we can anti-differentiate this straight away, because we can anti-differentiate z, because it's just z to the 1. So let's fix the constant to 81 over 4 pi, and the antiderivative of z to the 1 is z squared over 2. And we're going from 0 to 2. And as usual, we do top limit minus bottom limit. And I'll note there was no mention here of units, so we can't actually assume anything. We can't assume that it's kilograms or anything like it. So top limit 2 squared over 2 minus 81 over 4 pi 0 squared over 2. And the second term is obviously 0. And I think the 2 squared over 2 is 4 over 2 is 2. And then you can do 2 over 4 is a half, or whatever way you want to cut it. You get 81 over 2 pi. If you want, you can approximate it, but because there's no units, there's not really much value to that. So that should be enough to get you through everything. There's some more little examples there.